computer audio. I want to come down to this one. Okay. I have everything there. It's going to be, hold on. Okay. Hold on. Let me mic up. It's always something. Let's see if this works today. Okay, is it working? Yeah? Woohoo! Okay. All right, so attendance is up. If you want to go ahead and sign into attendance. And then ask me a question again. There are like so many. Oh, exam 4. What is exam 4 going to be on is the question. So I'm going to show you. So exam 4, like we just had exam 3. So exam 4 is only going to be on 8 and 9. And I'm going to show you why in just a second. Because if we scroll up, I think I'm going to design my Moodle page differently next time. I take suggestions. I totally take suggestions because I have no idea what I'm doing on Moodle. But I think it could be improved. All right, so if we come all the way down, right? You had an exam 4 here. Let me sign in and change it. This is what I wanted to do. Because I wanted to talk to y'all about this. I gotta go over again. Always something. All right, so what I decided to do was to take your exam 4 and put it here instead, okay? So the reason why is because, if I could zoom out a little, that would be great. Here we go. Okay, is that the last 2 days of school are supposed to not be exam days, and I didn't know that. And so that moves that your homework to being due on the Friday before exams. Okay, so we are over here. So let me come over here. We're over here. We just took an exam. We're starting chapter 8. You should have watched section 1, section 2, and section 3 videos, right? We're going to do the in-class problems today. Then Tuesday is going to be part 2. Oh, and we got something on the chat. I'm not planning a review day during class time. I'm still trying to figure out how to schedule something outside of normal class time. So I'm working on that. So then it'll be chapter 8, part 2. Then look at this, y'all. Please make a note. You have homework due on Wednesday. Normally your homework's due on Monday, but your homework is due on Wednesday, just because of how the exam fell. And now, like, we're off, right? So then it'll be chapter 9, part 1, chapter 9, part 2, homework due on a Wednesday again, and then it'll be chapter 8, oh, and this should be chapter 8 and 9 on exam 4. So exam 4 will again be only 2 chapters, which is a good thing. It's a good thing, okay? And then your lowest regular exam score will be dropped. And I'll try to do that weekend so that when we come back, you kind of have a grade. You know what your exam grade looks like. We'll do chapter 10. Why did it do that? Delete that. Okay. Then it'll be chapter 10, part 1, chapter 10, part 2. The chapter 10 homework will be due on Friday, and then we'll have our final exam week. Does that make sense? Yeah? Okay. Because these 2 days, y'all aren't supposed to have exams. So I went ahead and moved it just back a chapter. I figured that would help y'all out. It would be less material on one exam. Okay. Questions about that? Good. Okay. So my suggestion to you is we are in the home stretch. We are seriously in the home stretch, which means you need to come to class with those videos watched. Okay? So come back to this calendar and please make sure you watch the videos before you come to class. Class makes infinitely more sense when you have watched the videos ahead of time. Okay? Y'all know what I mean? Are we out of wipes? Are we out of wipes? No?
Oh, yeah, I'm sorry. I didn't hear you talking.
That's okay, but we are?
Yeah.
Yeah. Okay. If somebody wants to ask the person at the desk back there, and I'll text them and tell them that we need some more wipes. Let me do that real quick. Oh, I can do that while y'all are doing your eye clicker. That's what I'm gonna do while y'all are doing your eye clicker. Okay. So make sure you watch your videos. I updated your grades, so you have all of your grades up to date now. A lot of people wanted to know how their eye clicker points would affect their grade, and so I went ahead and put those in. But when I put those in, what a couple of y'all emailed me and said is, what you're seeing doesn't match what I put in. Like y'all are seeing a higher score than what I see. And so in iClicker, which I'm learning things about iClicker as well, there are two different kinds of points. There are, did you get the question right or wrong? And did you try? So for each day that you try, they give you like a point. But then they also give you a point for every correct answer. So I was looking at your correct, right or wrong. Did you get it right or wrong? Not at those, did you participate that day, right? So it shows it as two separate grades for me, but it shows it as one grade for you all. So what I'm gonna do is I'm gonna go ahead and give it to y'all. I'll give you that extra 1 point each day that we've been in class. And so if what you see in Moodle is lower than what you are expecting based on the percentage, sometime in the near future, in my spare time, I'm going to go through and recalculate everything and repost the grades again, but it's going to take me a little bit of time because it takes time. But so I want you to know it will be the percent that you see and not the one that I was seeing, but it's just going to take time for me to calculate it all again. Does that make sense? Yeah? Okay. Questions about that? Okay, good. All right. I think that's all my announcements. Oh, your joke of the day, right? You need your joke of the day. All right. So what is a witch's favorite kind of test? A spelling test. All right. I thought it was funny, especially because I can't spell. Okay, full screen. All right, so we're going to start with some clicker questions. These clicker questions pertain to Chapter 8, but they're a little bit of a review on the material that you need for Chapter 8. So if you've watched the videos, these are going to be super easy for you. If you haven't, you might get a few, but you need to watch the videos before you come to class. Okay, y'all ready? I'm stopping the attendance. We had 76. Why is it doing this? I did this another time. I don't understand. Like I can see them. How come I can see the question here and not see it there? Me and this computer are not getting along. Okay, let me try this. I have it a different way because I know it does it sometimes. All right, let's try it like this. Can you tell I'm a Mac person and not a PC person? Maybe. Can we open? The best laid plans, y'all. The best laid plans. Let's do this. Okay. Oh, yay. Okay, a single water molecule can make a maximum of blank hydrogen bonds. A minute and a half. Did I do something? What?
You started
It asked the question and then it went off.
It shows it running. Can y'all answer? Can you? You can or can't?
No, I can.
Oh, I didn't put on, oh, where'd it go? Oh, there. Sorry. I'm like, what did I do wrong? So many things. Okay, now we good? And I'll give y'all a minute 45, I guess, because I messed that up. Or once we get 76 responses, because we had 76 people. So we got 2 more. Oh, yeah. Oh, 77. All right. 78. Okay, 45, I'm calling it. All right, so how many did we say you can make? Oh, I wanted to do this. 4, should be 4. Should be 4. Why 4? It should be D, 4. These can be what? Acceptors. This is an acceptor. These and these are what? Donors. So we have 1, 2, 3, 4 possible hydrogen bonds. What's our golden rule of solubility? Like dissolves like. Water is a polar molecule. So what is going to dissolve in water? All right. Yeah, okay, and then I got to clear it. Okay. All right. So which of the following solutes would you expect to dissolve in water? A minute and a half. Oh, and we got a chat. I'm sorry. Okay. Ellen's asking, what's the last exam's average? It was a C. It was a C average. I don't remember the number, but it was a C average. Y'all remind me about the chat. Okay, we got 6 seconds. Okay. All right, so what are we looking for in something that will dissolve in water? What do we expect? What kind of molecule? A polar molecule. How do we get a polar molecule? We have to have what? Not necessarily hydrogen bonding, but we need polar bonds and an asymmetric molecule.
Why can't I sit over here? This is
Your sound.
I don't.
there's some nice weather over here.
Hold on. Okay. So, hexane. Do we have polar bonds in hexane? No, why not? It's just carbon and hydrogen. Carbon and hydrogen we signify as non-polar bonds. CCl4, do we have polar bonds? Yes, we do. Carbon and chlorine, chlorine's much closer to fluorine than floozy, right? So we have a polar bond, but tell me about the molecule. Is it symmetric or asymmetric? Right, C, and then we have 4 chlorines all around it. So if we have polar bonds, look at what happens to those polar bonds. What do they all do? They cancel each other out. So even though we have polar bonds, we don't have a polar molecule. So it can't be B, it can't be A. What about D? All what? Carbon and hydrogen. So can't be, so must be C. Good. All right. I think we need clear. All right. Oop. Okay. So a mixture which has evenly dispersed substances is called a blank mixture. Bless you. Ten seconds. So what did y'all say? Oh, very good. Very good. Homogeneous. Homogeneous is correct, right? Heterogeneous is something where you can see different chunks of stuff, right? It's not evenly distributed. Diluted, does that tell you if it's homogeneous or heterogeneous? No. And if it's pure, can it be a mixture? No. Okay, good. Awesome. All right, one more. Last one. Oh, I got to clear it. Okay, so you have a cup of coffee with sugar in it. You have stirred it, so it is a homogeneous mixture. Scientists call that a what? This one's from the video. Ten seconds. Okay, so what do we call that? Good, you should have said C. Good. A solution. A solution. What makes up a solution from the video? a solvent plus a solute, right? So what's the difference between a solvent and a solute? A solvent is the one where we have more of that substance. The solute is what we have less of, right? So what's the most common solvent there is? The most common solvent is water, right? And so this is how I remember solvent. I remember that it's water, and I remember that water kind of looks like a V, solvent, right? So water is the universal solvent. That's how I kind of remember which one is which. So if you find yourself a way to remember that, because we're going to say those words a lot. And so you have to get them straight in your brain. You really, really got to get them straight. Okay. All right. So let's jump over to, oh, now look, now it loaded on that one. That's weird. Now let's cross our fingers that this one works. Okay. I'm going to stick that over here. And, okay. Yay. All right. So remember our like dissolves like. So most organic substances, be careful with, right? Because they're nonpolar. So remember all the carbon and hydrogen molecules you looked at in that iClicker question? They're not going to dissolve in water because they're organic. Remember, organic is carbon and hydrogen. So be careful that you understand that those organic substances usually do not dissolve in water. Okay, so let's try to look at some examples and see if we can figure out what is the solute and what is the solvent. So helix, this is a breathing gas that's really kind of cool. It's 79% helium and 21% O2 for patients who have difficulty breathing. Have y'all heard of this before? Anybody? So what is the atmosphere usually? This is just kind of a side note. I just thought this was cool. It's usually nitrogen. It's usually about 80% nitrogen, and then oxygen, O2, into an O2, is usually 20%, right? That's like the normal makeup. You got some other stuff in there, but those are the two big ones. So I'm kind of rounding those numbers. But in helix, right, and in normal air, helium's about 0.0005%. Like it's tiny. It's a tiny amount. But in helix, you have all of this helium. So if you compare the mass of nitrogen and the mass of helium on the periodic table, which one has a higher mass? Go look right now. We'll pull up a periodic table and look at nitrogen and helium. Nitrogen is 14.01, right? And helium is 4.003. So which one's heavier? Nitrogen or helium? Nitrogen's heavier. So the body has to work harder to exhale something that has a lot of nitrogen in it than something that has a lot of helium in it. We don't use the helium. It's just in the mixture. And so what we can do is we can make this solution of air for these patients to where if they have breathing problems, because the air, the helix, right, is a lot less dense, it's easier for them to exhale. So it's kind of a cool thing. All right, so, but the question is not what is it? The question is which one is the solvent and which one is the solute? So which one's the solvent? Helium is the solvent. Whichever one is in higher concentration is the solvent, and which one is the solute is the one in lower concentration. Okay. B, children's Tylenol oral suspension containing 160 milligrams acetaminophen per 5 grams of water. Which one is the solvent? Water, 5 grams of water. So water is the solvent. What is the solute? Acetaminophen. Okay. All right, so a small amount of an herbal remedy dissolved in alcohol. Which one is the solvent? Alcohol. And then which one is our solute? Our herbal remedy. Okay, so all you're looking at is what's more and what's less. But you have to remember what's solute and what's solvent. Like that one, that's the big trick that that will trip people up. Okay, so remember when we were saying we had a homogeneous mixture? And what did we call as scientists a homogeneous mixture? Homogeneous mixture, right. So it's a solution, so we call it, and so the requirements for being a solution, right? You have to be consistent, right? Consistent composition. What else? That's not the only thing. If you remember back to the lecture video, what else did we say had to be true to call it a solution? There was a list. Yeah, there's no chemical reactions. What else? It wasn't the only thing. It has to be transparent. What else? Does not separate. So like, it doesn't matter how long you put this solution out on your table, it will never separate, right? But that's assuming that there's a cap on it, right? Then otherwise you'd have evaporation and things could happen. But we're assuming a cap is on it, then nothing would happen. So there's no separation. Okay, so there were a couple of different things that could happen if you mix stuff together. You could get a solution. What else could you get? A colloid, C-O-L-L-O-I-D, right? Colloid. So what's the difference between a solution and a colloid? You can't see through it, right? So not transparent. What was the example in lecture for a colloid? Not muddy water. Milk. Milk. If you have milk and you put it in your fridge for a week, is it going to settle? No. Now, I'm not talking about curdle. That's a chemical reaction. I'm talking about just settle. Do you have to shake your milk before you drink it? No, not unless you're drinking soy milk, right? But if it's a colloid, right, it does not separate, right? So it's like a solution that you can't see through. Why can't you see through it? Because the things inside of that colloid did not dissolve. So you have proteins, fats in there that are non-soluble. They're evenly dispersed, but they're non-soluble. What's my last classification? When y'all said muddy water, that was a good example. Muddy water is a suspension. Out of room, a suspension. And I'm not saying that you have to go home because you're in trouble at school. A suspension is when you mix things together and the particles are so big that gravity is going to actually act on them and pull them down. So this will settle. Separate, whatever you want to say. Okay, so now that we know the properties, can we identify the following as solutions or colloids? So a 5% albumin, a protein 4 replacement fluid. What's albumin? It's an enzyme, it's a protein, right? So it's made out of amino acids and things like that. It's organic. Guess what? It does not dissolve. So proteins do not dissolve. Proteins, fats, right? Protein, fat. That stuff does not dissolve. So if it does not dissolve, it's got to be a colloid. Okay. The electrolyte replacement for fluid, lactated Ringer's solution. It's an electrolyte. Tell me about an electrolyte. This you have to bridge what we learned last unit with what we're learning this unit. What's an electrolyte? I'm going to have a Gatorade, and that Gatorade says on the bottle, 5 essential electrolytes, and then you spend more money on it. What did they put inside of it? Salt, ions, right? Okay, so what's an electrolyte? It's an ion. An ion is a charged particle. Do charged particles interact with water? In what kind of an interaction? A dipole or ion dipole or dipole ion, however you want to say that, but an ion dipole interaction, right? Okay, because they're charged. So like dissolves like, what's going to happen? It's going to dissolve, so we have a solution. You have to apply what you learned before. Okay, D5W, a 5% dextrose IV fluid. What did we learn about sugars? What do they have on them? What do they have on them? Hydroxyl groups, right? Functional hydroxyl groups. Those functional hydroxyl groups are, guess what? They're polar, right? They make that molecule polar. So are they going to interact with water? Absolutely. Think about this. If you put sugar in water, can you see through it? So what is it? A solution. Use your common sense as well. Don't just use the chemistry that I'm teaching you. Use your common sense. You know that. Dextrose, we know now know is a sugar. You know what happens with sugar and water. You got that. Okay? All right. Okay. Oh, I took up room. That's okay. All right. So now, once we have our solution, well, that's not what I wanted to do. Once we have our solution, we need to know, is it saturated or unsaturated? So anybody have a family member who makes that homemade tea, you know, where you boil the water, you get the tea bags out, you pour your really hot water on top of your tea bags, and at the same time, while that water is still hot, what do you add? You add your sugar, right? Why do you want to add it while it's hot? So it'll all dissolve, because if it's classic iced tea, right? It's got lots of sugar in it. And so you actually add so much sugar that it's to the point where it's saturated. You have the maximum number of sugar molecules inside of however big your volume is of water, right? Now, if you want it all to go in solution, if it's at that saturated point, what you're going to have to do is increase the temperature. So then you can make all those sugar particles dissolve. That's one thing that controls solubility. So if something is saturated, it's holding the maximum number of particles. If it's not saturated, you could put some more sugar in and it's still going to dissolve. What happens when you get past the saturation point? It starts to settle because it's not all dissolving. So what happens in that point is that you constantly have some particles that are dissolving and then some particles that are called precipitating out. They're becoming solids, but they're still in the liquid. And it cycles, right? It's an equilibrium. Okay, so let's look at these and see if we know if we have a saturated solution or not. A piece of rock salt that does not change in size when added to a salt solution. So we have a container of water. It's got salt in it already. And I put a hunk of rock salt in. It doesn't change. It's already saturated. It doesn't dissolve because it's saturated. A teaspoon of honey that dissolves in hot tea. You could put another teaspoon of honey in that tea, so it can't be saturated. So not saturated. Okay. So when we talked about the T, right, we said that if we increase the temperature, we can increase solubility. But that is only true for things that are solid. If you want to put a solid into a liquid, if you raise the temperature, it's going to happen more easily, right? But what about a gas? It's not true, right? If you have a can of Coke, right, and it gets hot, what's going to happen? It's gonna actually expand in size, and it could burst. It could, if it gets hot enough, it's gonna blow up, and it's gonna be a really, really big mess. If it just gets kind of warm and you pop the top, you get a big, right? But what if it's cold? You hear it, but you don't hear it quite as loudly, right? Okay, so that's telling us that as we increase the temperature, what's happening to those molecules of gas that are inside of your cola, your soda, right? Try not to market anybody's product. What's happening to those gaseous particles? Your soda is what? Liquid and a gas. What's the gas inside of your carbonated beverage? It's got carbon in it, right? CO2. CO2. All right, so when I heat that beverage up, what's going to happen to my gaseous particles? They're not going to dissolve in the liquid anymore, right? They're going to actually go into the space, the air space, and they're going to start creating more pressure, right? Because you have more gaseous particles in the same amount of space, and they're going to put pressure on things that are inside of it, and that's why the can will explode, right? So for a gas that's dissolved in liquid, what happens as we increase temperature? What happens to solubility? It's going to go down. So a solid and a gas are opposite one another. Make sure you think about your soda and your iced tea, and then you can figure it out. Just have to remember your soda and your iced tea. Okay, so if the temperature of a solution decreases, the solubility of a gaseous solute will do what? So the temperature drops. What does our solubility do? So this is my soda, and I put it in the fridge, right? What's going to happen to my solubility? It's going to increase. C-R-E-A-S-E, right? If I let's just say I'm sitting down, you know, I got home and I want to have a nice Diet Coke. I do like a Diet Coke every now and then. And I sit down at my table and I pop that top and I'm about to enjoy my Diet Coke. And Charles says, "Oh, Mom, let's go outside," right? And I want to come back to a nice Diet Coke. What should I do with that Diet Coke? Put it in the fridge, because if I leave it out, what's going to happen? It's going to go flat. What does go flat mean? All the carbon dioxide is going to leave my can of soda. And when I come back, I'm going to take a sip and go, "Oh, man." But if I stick it in the fridge before I go outside and play, I'm going to come back and reach in the fridge, and it's going to be pretty close, right? Some will escape, yes, but it's going to be pretty close because that gas is still soluble inside the liquid. Okay, so when you think about solubility, I want you to think about real world examples. That's what's going to get you through. All right, so if the temperature of a solution decreases, the solubility of a solid solute, so let's say this is sugar, can't even spell sugar, and this is water, all right? What happens when we increase the temperature of water to the solubility of our sugar? Increase or decrease? Or stay the same? The temperature goes up on my liquid and I put a solid in, my solubility is going to increase. Oh, I'm sorry. Thank y'all. Will decrease. Sorry. Would help if I would be able to read. All right. If the pressure above a solution decreases, the solubility of the gaseous solute will do what? All right, now this is them manufacturing my Diet Coke, right? How do you make a Diet Coke? How do you get that gas inside of the liquid? You force the carbonation in with high pressure. So the more pressure you have, if the pressure above the solution increases, then your solubility is going to increase. So let's look at our question. If the pressure above a solution decreases, that's like me popping the top on my Diet Coke. I decreased the pressure. What's going to happen to the solubility of my gaseous solute? It will decrease. Make sense? Always related back to a Diet Coke. I don't know what to tell you. All right. Here we go. All right, explain what is happening in the following situations in terms of solubility. Fish die in a lake that is heated with water from a power plant cooling tower. This actually happens. So what's going to happen? If we increase temperature, what gas is important to fish? Oxygen. Fish need to breathe too. How do they breathe? They have oxygen that's dissolved in the water. So as we increase the temperature, we're going to decrease the solubility of oxygen in the water. Fish don't breathe, fish die. It happens. Like you'll come one day and there'll be a mass of fish like floating because they're dead. So it's very important that we monitor and make companies accountable for the things that they do. All right, B, crystals form in a jar of honey that has been sitting for several months. The seal is broken, I will tell you that. Right, what's happening here? If I put a bottle of water on my counter, what's going to happen to that water? It's going to evaporate. It's going to absolutely evaporate, right? And there's only so much sugar that any solution can contain. Well, honey is mostly sugar and water, right? So if I leave something out and some of that water evaporates, what's going to happen? We're going to go from not all the way saturated to all the way saturated and then past the saturation point. So what's going to happen is that we're going to decrease our volume, right? Which makes the solution becomes saturated. And then you have sugar precipitating out, or sugar crystallizes. Okay, the last one. A person receives oxygen through a breathing device. When you receive oxygen from a breathing device, is it the same concentration of oxygen that we breathe normally? No. We give them a higher concentration, right? So you get a higher concentration of oxygen, O2, right? When we talk about pressures, the way that we talk about their concentration, the higher the concentration, the higher the pressure exerted by that gas because there's more there, right? So what's going to happen in terms of pressure if we increase the amount of O2 given to a patient? Getting all this wrapped up. So we're going, if we increase the concentration, what happens to our pressure? We just said it, it goes up. So we increase pressure of O2 that goes where? Into the lungs, right? So then what's going to happen? Where does oxygen have to go in order for someone to survive? You breathe it into your lungs, but that's not where it stays. Where does it go? It goes into your bloodstream. So your blood is, guess what, mostly It's a liquid, mostly water, right? So the blood has to dissolve into the liquid of your blood, and then it gets picked up by red blood cells that are inside of your blood. But it first has to dissolve into the liquid. So if we increase the pressure, what do we know about the solubility of O2 in the blood? Increase or decrease? Solubility of O2 in the blood. Increase or decrease? What do we say? Increase. Right? That's the whole point. We want these patients to get more oxygen. So to give them more oxygen, we put a richer concentration of O2 inside of their, you know, the little things that go in their nose. I know there's a scientific nose for that, but I don't know what it is. Microphone's off? Oh, low battery. Y'all. It's just me. We run out of lights. The battery always dies. Okay, testing. All right, yay. Okay, so I don't know what y'all heard and what y'all didn't hear, right? But as we increase the amount of air, the amount of oxygen inside the air that we give patients, right? That means that we're increasing the pressure from just O2. So more O2 will move into the person's bloodstream. Therefore, it's more soluble, right? So pressure and solubility are interrelated for our gases, okay? Good? All right. So what do we got next? All right. Oh, this is cool. Hyperbaric chambers. So a hyperbaric oxygen chamber contains 100% oxygen instead of the normal 20%, right? So these chambers can be used to reverse the effects of carbon monoxide poisoning in the bloodstream faster than what would occur in normal air. Based on Henry's law, which is, I don't care that you know whose law it is, but based on the relationship between pressure and solubility, how is this possible? So if we increase our percent of O2, what's going to happen? Increase the what? We increase the pressure, right? Because Henry's law, we're all talking about pressure and solubility. So we got to talk about pressure. So if we have a higher pressure, sometimes they call it PO2. That's the partial pressure of O2. Okay, so what happens if we increase the pressure from O2? We just said it, y'all. More O2 is going to dissolve in the bloodstream. And I don't know if y'all know this, but oxygen and carbon monoxide bind in exactly the same way inside of red blood cells. So they bind to hemoglobin, and hemoglobin has like 4 spots that it can bind to oxygen molecules. And so if you have carbon monoxide bound, it won't bind O2, right? So what we try to do is basically outcompete the carbon monoxide. We give the person so much O2 that their red blood cells, or hemoglobin in their red blood cells, the only thing that it can replace the carbon monoxide with is O2, right? So that'll happen faster in a hyperbaric chamber than in a normal environment because you have more O2, so you have more pressure. So it happens faster in a hyperbaric chamber because you have more pressure. Make sense? What do we say? So more O2 will dissolve in the bloodstream and replace the carbon monoxide, CO, in the blood more quickly than in regular air. Okay. All right. So now we're going to talk about how solutions actually form. Like we got the big conceptual stuff. Now we have to kind of look at the chemistry of it. And this is going to be really important for the following sections in this chapter. So there are a couple of different things that can happen when you put solutes into a solvent. And we haven't discussed that yet. So if you have, let's say, NaCl, let me go back one and give myself a little room and we can, isn't there a, make it bigger, but apparently not. I thought there was. There it was, extend page. There it is. Okay. So what happens when we put something in water or in a particular solvent will depend on what it's composed of, right? What if we have an ionic compound and we add water to it? What's going to happen? It will dissolve. It will dissolve fully. So if you have NaCl and you put it inside of water, and the way we write it is like this, what's going to happen? All of our water molecules will orient so the positive, partially positive hydrogens will get close to the chlorine, right? And the partially negative oxygens will get close to the sodium and will completely break apart that whole salt molecule, that whole salt piece. And you'll end up with sodium ions and chlorine ions. But what's important when we write these equations out is that we say we started with a solid and we're ending with these ions. They're not solid anymore. They're in water. So we call them aqueous. So this is something that undergoes a full dissociation. So it completely dissolves. Does everything do that? No, not quite. Not quite. There are things that have charges that don't completely disassociate. So do you remember when in the last chapter I asked you, what are the functional groups that can have charges? Do you remember that? What are the functional groups that can have charges? Protonated amines and carboxylic acids. Very, very nice. All right. So let's look at one of those. Let's look at a carboxylic acid. So if you have a carbon to an oxygen to a hydroxyl and some R group, right? Okay. What happens when we turn it into the charged form? Get oxygen's negative and the hydrogen becomes positive. So this happens in water, but not every single molecule is going to disassociate, only some of them. So instead of writing a full arrow, what we write is our back and forth, our equilibrium arrow, because really this only happens a small portion of the time. It only occurs generally not so often, right? Most of our stuff is in this neutral form, but it's in water, right? So this is our partial. So this is an example of a partial or partially disassociated. Okay. Now, the last one, what if it doesn't disassociate? Can you have something dissolve and not disassociate? What is the difference between dissolving and disassociating? I know it's two Ds and they sound really familiar, they sound really similar, but they're not. Disassociate means what? They're breaking up. They're breaking up. So you form charged species. They break up because they break up. Okay? So disassociated is not the same thing as dissolved. Can you have something that dissolves and does not disassociate? Absolutely. And we talked about it today. Sugar, right? Here's our sugar. Doesn't matter what sugar it is, right? What happens when I put this in water? It dissolves. We started off as a solid. If you want to write it, if you don't want to draw the picture, you could just write C6H12O6 and it's a solid. We put it into water and what happens is that it's still C6H12O6. The structure didn't change, but it is now aqueous. It's dissolved, but it's not disassociated. All of those hydrogens are still attached. Okay? Use your common sense. You know that sugar dissolves in water. Now you just have to know that it doesn't disassociate. Okay? Yeah? All right, so let's go on. Do this. All right. Predict whether the following will fully disassociate, partially disassociate, or not when dissolved in solution. So sodium sulfate, Na2SO4, a strong electrolyte. What's an electrolyte? An ion. An ion is charged. Okay, so sodium sulfate, a strong electrolyte. What do we say? Fully, partially, or not? Fully. Fully. Okay, how about ethyl alcohol, CH3CH2OH, a non-electrolyte? It will not. It will not form an electrolyte. It is not charged. Hypochlorous acid, a weak electrolyte. Weak is telling us that it's going to partially disassociate. So that's that equilibrium arrow, where some of these hydrogens will pop off and some will not. Okay, so now we're going to go down and we're going to do those same substances and we're going to write a balanced equation for the hydration. So just what we were doing before. So if we have Na2SO4 solid and we put it in water, we have to know what it's going to form and is it going to be an equilibrium arrow or a solid arrow? Okay, so what do we think about this? What kind of substance is Na2SO4? Na2 is a, well, Na is a metal, right? SO4 is a ion. So what's a metal and a polyatomic ion? Right? You could have a metal and a non-metal, a metal and a polyatomic, or a polyatomic and a polyatomic. Any of those combinations gives you an ionic compound. An ionic, ionic. What do you think is going to happen? It's a strong electrolyte. We're going to make ions. All right. So what's going to happen? They're going to disassociate. All they have to do is break apart. So go on the periodic table and find sodium. Where is sodium? I'll give you a second. Go pull up the periodic table. It's in group 1. It's in the first column. So what should my charge be on sodium? +1. Now it's in water, so I got to say it's aqueous. And then I need my polyatomic ion. It's aqueous, but it's an ion. So what's its charge? Do you need to memorize that? No, you do not need to memorize that, right? If you look on, where is it? Right, this is your stuff you get on your exam. Come down. Oh, look at this, polyatomic ions. Yay, right? You don't have to memorize them. You just need to be able to go find them, okay? So I don't even remember which one we were doing. Where are we? SO4. So what's the charge on SO4? 2-. Okay. Anytime you write a chemical equation, you are going to check to make sure it is balanced. Is it balanced? It is not balanced. How can I balance it? A 2 in front of the sodium. Now my equation's balanced. Okay, let's do B. Ethyl alcohol. CH3, CH2OH. Now this is telling me it's a liquid. So I'm going to put it into water. It's a non-electrolyte. So is it going to break up? No, but I need to say in some way, shape, or form that it's in water. So I have the same exact formula, but instead of putting liquid, what do I put? Aqueous. All right, and then my last, oh, and my balance. Yes, I didn't change anything. All I changed was what's back here. And do I need a solid arrow or an equilibrium arrow? Just a regular arrow. Okay, how about C? Hypochlorous acid. What is it? A weak electrolyte, so it's going to partially disassociate. So if it's partial, I need to make sure to put my equilibrium arrow and say that it's done in water. And what's going to happen? It's going to break apart. Usually what's going to happen here is the hydrogen is going to come off. So if we have a hydrogen, if we take away the hydrogen, and that's aqueous, what's left? The ClO, right? So where do you think I might find ClO? If the hydrogen broke off and the hydrogen is positive, we know that both sides of the equation have to be neutral. And so if we have a positive H, and we have to have a charged ClO. So where are you going to go to find that charge? Not the periodic table, because we have 2 elements. We have chlorine and oxygen, so it is polyatomic. So we're going to go to our polyatomic table, and where do you find ClO? It's a -1. Okay. And do our charges balance? Yes. Do our number of atoms balance? Yes. So we are good. We are good to go. All right. Getting close to the end. How many more do we have? Not too many. All right. So we have a few more where we're doing hydration. We're told in 818 for the following ionic compounds, write a balanced equation for their hydration in water. So what do we know about all these? They fully disassociate. Okay, they fully disassociate. So let's start with A, FeCl3. I'm going to put it into water. Oh, and I got to put that it's, what is it to start with? It's going to have an ionic solid. and we put it in water, and then what? It dissociates, right? I have a metal, here's my non-metal. So it's going to disassociate into iron and the chloride ion. How do I know my charge on chlorine? From the periodic table, right? It's in group 7, 17A, 17 or 7A, excuse me. So it's -1. Now how about iron? Yeah, we don't know because it's a transition metal, right? So we have to look at the formula to figure it out. So it's basically the reverse crossover. Because chlorine's a -1, right? That means that Fe would be a 1, so that checks out. So then reverse the 3 and put the 3 as the charge on iron. So it would be 3, but we know it has to be positive because to be ionic, we need a positive and a negative. So that would be a +3. Now I have to worry about states of matter. I put it in water, so I must list them as aqueous and chlorine, aqueous. Okay, am I balanced? No. What do I need to do? A 3 on chlorine. Now my atoms are balanced, my charges are balanced. I'm good. Okay, B, NaHCO3, and it's a solid. We know it fully disassociates in water. What happens? It's going to separate right there. We have a sodium that's going to come off, and then HCO3 is going to be in the polyatomic ion table. So we're going to go, what's our charge on sodium? +1. What's our charge on HCO3? -1. And we're going to say that these are aqueous because they're in water. And then tell me about my balancing. Am I balanced? Yeah, I'm balanced. I'm balanced. Okay, let's do C. K2SO4. It's a solid. We're going to put it in water. What's going to happen? The potassium's going to jump off. So we're going to have potassium. What's the charge on potassium? +1. It's aqueous. The rest of it is SO4. Go look on your polyatomic ion table. What do you get for SO4? Minus what? -2. -2. -2. Okay, am I balanced? I'm not balanced. What do I need? A 2 in front of the K. All right. Okay, last one. CaNO3, 2. We're going to do it in water. Does the 2 on the K carry over the 1 on the bottom? What do you mean? This 2 or this 2? This one. Does it carry over? I don't know what you mean by carry over. After you put the water, you have to look at the individual atoms. You can't just arbitrarily put a subscript. You can't change subscripts. The only thing that you can change is a coefficient. So the subscript is as it was given, right? But your coefficients are what you can use to balance the equation. So you can't put K +2 because that would be like a potassium atom in a covalent bond with a potassium atom. And that doesn't happen, right? They're ionic. Okay. Does it make sense, Sarah? Okay, so CaNO3 2. So what's going to happen? Calcium comes off. Go look and find your charge on calcium. Plus 2, we're going to put it as aqueous. And then we need our polyatomic ion, which is NO3. What's my charge on NO3? It's a -1. And then this is aqueous. Am I balanced? No. Okay, so the only thing I can change are coefficients. So what am I going to do? If I put a 2 in front of the NO3, now I'm balanced. Okay. All right. Now, we did lots of conversions, however many chapters ago that was, right? When we went from grams to moles and all that kind of stuff. There's one more conversion that you need to know, and this is really important for the health field. So a lot of times it doesn't necessarily matter what ion you give to someone. What matters is how much charge is there. So think about like potassium. What's the charge on potassium? +1. What's the charge on calcium? +2. So you can have one atom of potassium and one atom of calcium. And even though you have one of each, you have double the amount of charge on the calcium than you do on the potassium. And so that's really important because your body handles charges based not on the atom, but the amount of charge. So it's really important to know when you're giving someone an IV fluid filled with some kind of an ion, not only how many moles of substance is dissolved inside of that IV bag, but also how much charge is there. And so that's where we use this term called equivalence. So what we want to know is how many charges are there. Well, that depends on the charge of the individual atom, right? So if you have Mg2+, and we have a solution that is 2.50 moles of Mg2+, how many equivalents, so how many charges are there? Well, dimensional analysis, right? Remember I said it wasn't going away? It's really not going away. So what I know is if I have 1 mole of magnesium 2+, how many moles of equivalent charge do I have? I have 2, right? Because for every 1 atom, I have 2 charges. So if I have 1 mole, I have 2 moles of charges. So I have 2 equivalents Mg2+. So what do I get? 2.5 times 2 is 5 to 3 sig figs equivalents Mg2+. So a lot of times it's not what ion it is, it's how much charge is present inside of that IV bag. All right, last problem of the day. All right, in this case, we have a 5% dextrose IV fluid. So if you're going to give someone an IV bag, you have to make sure that what you're giving them is similar to what's inside of the body, or you're going to start killing their cells. And we're going to find out why. You're going to find out when you watch the videos for the next couple of lectures, right? If it's not right, either the cells are going to explode or they're going to shrivel and die. So it's very, very important that you give them the right concentration of stuff. So you have to give them sugar and you have to give them ions. And so we add dextrose for our sugar, and then there are some other ions that you could do, but potassium is very common. Okay, so we have a 5% dextrose and we have a 35 milli equivalent. What's the difference? What's the relationship? What is milli? 1,000. So in 1 equivalent, we have 1,000 milli equivalents. Just like in 1 mole, we have 1,000 millimoles. It's the same relationship. Okay, so we have 35 milliequivalents of potassium ion per liter of solution. If a patient receives 250 milliliters of the IV solution, how many moles of potassium were delivered? All right, so start with what you know. What do we know? 35 milliequivalents of potassium. Per what? They received 235 milliliters of solution, right? Oh, no. I'm sorry. I was not even looking over here. Look, per liter. I was looking at my equivalents. My Q covered it up. Per liter. Sorry. Okay. So I have 35 milliequivalents of potassium per liter. I want to know how many moles. So I need to get out of equivalents and get into moles. So what do I need to do? Let's convert out of milli first. I have 1,000 milliequivalents in one equivalent. Then I have some number of equivalents of potassium in 1 mole of potassium. How do I know what this value is right here? It depends on the charge, right? So if it's a +1, it's going to be 1 equivalent. So now what are my units? My milliequivalents canceled, my equivalents canceled. Now I'm in 35 moles per liter. But did I give them a whole liter? No, I didn't give them a whole liter. So now what? In 1 liter, I have 1,000 milliliters, right? So now I'm in moles per mil. Now I can just multiply times however much I gave them, 235 milliliters. So my milliliters will cancel. You can put it like that. And what do you get? 35 times 235 divided by 1,000 divided by 1,000. Should be pretty small. Make sure you put it in your, look, you think I'm being silly. In class, you need to put it in your calculator, because if you don't do it now in your calculator and you get home, you're gonna be like, how did she get that? 0.0082 is what I got. Is that what you got? Okay. So make sure you can put them in your calculator. All right, you have 4 videos to watch between now and Tuesday. The last 2, I don't know, YouTube was giving me some problems, so I'm going to try and go re-upload this afternoon. I don't know. Me and YouTube had a problem, but 2 of them are up, and I'll get the others up this afternoon. Have a good weekend. Woohoo! All right, anybody on the chat have a question? Yes, thank you, Aaron. I wasn't looking at the chat. Okay, if nobody on the chat has questions, I'm going to go ahead and end. All right, y'all have a good rest of your day.